This is Chemistry Unit 6, and in the last video we talked about electronegativity, which is a measure of how much an atom will attract electrons towards itself in a chemical bond, in a covalent bond. And we had this table up here. It's a periodic table with the Pauling scale values, or how electronegative is an element. And remember, the trend says going to the right and going up will give you the most electronegative elements. And then the bottom left is where they are the least electronegative. So we're going to use these numbers and look at our next concept, which is polarity. So what happens when two atoms with different electronegativities form a covalent bond? So we already talked about electronegativity. They're going to share unequally. So we'll need to compare the electronegativity of each atom. If the difference is small, as in less than 0.5, the atoms will share the electrons equally. When we're sharing equally, a covalent bond is going to be called nonpolar. So let's look at just a few examples here. So for instance, when carbon and hydrogen form a covalent bond, and here I'm just representing one bond between the two atoms. It's likely that there would be other stuff going on in a molecule, but we're just looking at these two elements and this particular bond. So if I look, I need to compare these values from the table above. So if I look up here, carbon has a value of 2.5. So we'll write 2.5 here. And hydrogen has a value of 2.1. And we look at the difference between them. And the difference between 2.5 and 2.1 is 0.4. And that would be less than 0.5. So we could classify this particular bond between carbon and hydrogen as nonpolar. We could also look at a bond between carbon and bromine. So again, we're looking at the electronegativities. We already looked up carbon, and it had a value of 2.5. And then we find bromine. Bromine is here and has a value of 2.8. And the difference between these two numbers is 0.3. And that is less than 0.5, which means that this particular covalent bond is nonpolar. So a hydrogen to sulfur bond. So we already looked up hydrogen. It had a value of 2.1, and sulfur is here. It has a value of 2.5. And the difference between these two numbers is 0.4. Less than 0.5 means nonpolar. Not every covalent bond is going to be nonpolar. So if the difference is greater, if the difference is between 0.5 and 1.7, then the more electronegative element will attract the electrons in the covalent bond. What happens is these shared electrons will spend the majority of their time closer to the more electronegative element. And the electrons that are pulled towards this atom, the more electronegative, gives it a partial negative charge. Now, it's not a real negative charge. It didn't just take the electrons and keep them. But since they spend so much time over there and the electrons are negative, it makes that area negative, a little bit negative. The less electronegative element will have fewer electrons at any given moment, so it will have a partial positive charge. And the covalent bond between these two atoms is called a polar covalent bond. Because one atom is partially negative, and we draw it like this, and the other one is partially positive. So this looks like an S. It's actually a Greek letter, and it looks more like this. It looks very close to an S, but it's not quite. A polar covalent bond is the result of unequal sharing. So if you wonder why this is called polar, and you understand that it has a positive and a negative end, partial positive and a partial negative end, you might think of something like a magnet, which has a north end and a south end. It has two poles. Or maybe if you think of something like this, and this is the Earth. It has a north pole and a south pole. It just means two opposite ends. So we look at a few different covalent bonds. So let's look at a covalent bond between carbon and oxygen. So carbon, if you look back to the previous page, you'll find that it has an electronegativity value of 2.5. And if you look back at the previous page, you'll find for oxygen that this is 3.5. We want to look at the difference between these two numbers, and in this case, the difference is 1.0. It's between 0.5 and 1.7, which makes this particular covalent bond polar. Here's a covalent bond between a hydrogen atom and an oxygen atom. Hydrogen, from the previous page, is 2.1, and oxygen is 3.5. And the difference between these two numbers is really quite large, 1.4, which puts it really towards the upper range of being polar. And this particular covalent bond is important because water is made of two of these bonds, and water is highly polar. And it explains a lot of the unique behaviors that water has within the chemical world. Let's look at sulfur to fluorine. Sulfur, looking at my table, has a value of 2.5, and fluorine has a value of 4.0. The difference between these is 1.5, which makes it polar, and this one is also towards the upper end of polar. This is a very polar covalent bond. If the difference in electronegativity is large, as in greater than 1.7, the chemical bond will not be covalent because the more electronegative element is pulling the electron so hard that it will not share at all, and the resulting bond ends up being ionic. So I'll just give you one quick example. So if you look at sodium chloride, it forms an ionic bond, not a covalent bond. And you'll notice I didn't draw a line between them. A line would indicate covalent bond. These two are just up here. So the electronegativity for sodium is 0.9, and chlorine is 3.0. The difference here is 2.1, which is greater than 1.7, meaning it's going to be ionic. So a polar molecule has covalent bonds that makes one end of the molecule partially positive and the other end of the molecule partially negative. So we haven't worked on drawing these types of diagrams before. I'm going to give you a preview of some things to come. So if we want to represent water and we want to actually see its covalent bonds, it would look something like this. We have an oxygen, and it is covalently bonded to two hydrogens. And then it has two pairs of electrons that it is not sharing. And so what happens, we look up just a little bit. Hydrogen is not very electronegative. Oxygen is very electronegative. So there's going to be polar bonds here. This one is polar, and this one is polar. So the end up here by the oxygen ends up with that partial negative because it has these 4 electrons, and the electrons in each of these bonds tends to spend more time closer to the oxygen. So we end up with a little bit of a positive end, which makes all of this have a partially positive because the electrons are going away from it, and it leaves it with a lack of electrons, which would be positive. Another way to show this is with this little kind of arrow here. And the arrow shows the direction that the electrons are going. It points towards the more electronegative element. And then it's got a little cross here. So you've got like this plus sign with the arrow pointing towards the more electronegative element. Here's another one. Arrow towards the more electronegative, partial positive, and has a little bit of a plus sign. So let's look at a different molecule, and this is actually not a binary molecule. Remember, a binary molecule has 2 different elements, could have more than 2 atoms, but this has 3 different elements, and so it's not a binary. Not something we would normally work with in this particular class. So here's how it would look. It's a carbon, 4 covalent bonds, or excuse me, 3 of them go to hydrogen and 1 covalent bond goes to the fluorine. So we have to look at each of these bonds individually, carbon to hydrogen and carbon to fluorine. So if you look back on the previous page, we find that carbon is 2.5 on the Pauling scale. Hydrogen is 2.1, fluorine is 4.0. So the carbon to hydrogen bonds have a difference of 0.4, which makes each of those nonpolar. So this bond is nonpolar, this bond is nonpolar, and this bond is nonpolar. But this carbon to fluorine bond has a difference of 1.5, which puts it in the polar range, which means this fluorine is going to be pulling the electrons and attracting them to itself. And they're going to end up over here by the fluorine, which means the rest of the molecule ends up with that partially positive. And if we were going to draw the arrow, it would look something like this. Positive end, and the arrow points towards the partially negative end.